Good morning, everyone. We shall continue our discussion on LL1 parsing in this class. In the last class, we have seen how we construct first plus one sets and what is the intuition behind the definition of the first plus one sets. The idea here is during the parsing time, if the current stage of parsing is this. So far, you generated the prefix u and a is the current look ahead symbol. And this is the derivation process, the derivation u, a, alpha. In terms of derivation, from the start symbol s, we made progress till this point. So now we want to figure out among the n available substitution rules for the non-terminal symbol a, which one we should use. And what is the idea? The idea is if the current look ahead symbol a belongs to first plus of a goes to alpha I, then use the substitution rule a goes to alpha I. This is the basic idea. And we say that a context-free grammar is LL1 if there exists no two substitution rules, a goes to alpha I and a goes to alpha j, or in other words, for every two substitution rules, a goes to alpha I and a goes to alpha j, if their intersection, if it is empty, then we say the context-free grammar is a LL1 grammar and it is amenable for LL1 parsing. That is, we can construct a top-down parser for it with no backtracking. So this is a grammar which is bugging us for quite some time. We will try to understand this grammar towards the end of today's lecture. In terms of recursive descent parsing, so we have seen, given a context-free grammar, for every non-terminal symbol in the context-free grammar, we can construct a function. We can construct a function. And then these functions associated with the non-terminal symbols, they call each other in a mutually recursive fashion in order to parse an input stream. And if you look at the structure of the function for a given non-terminal symbol, it will be like this. Step one is the most important step. So in step one, we have to pick one substitution rule in order to go ahead with the derivation process. The first approach is we non-deterministically pick one of the available substitution rules. But in practice, we don't have the power of non-determinism. So what do? We try out all possible substitution rules and check which one works. But when we try out all possible substitution rules, we may have to do backtracking. And in order to avoid this backtracking, what do we do in step one? We use the substitution rule a goes to alpha I if the current look ahead symbol a belongs to first plus of a goes to alpha. This is the case. And if there is one more substitution rule, a goes to such that a belongs to a goes to alpha j, then we are in trouble. If this is the case, we are in trouble. The grammar is not LL1 parsing. This is the summary idea. So now what we will do is, in order to construct, given a context-free grammar, in order for us to be able to construct an LL1 parser, we should compute the first place sets for various substitution rules in the grammar. In order to construct the first place sets, we need the first function, and we need to know how to compute the follow function. So in order to compute the first place sets of various substitution rules, we need to know how to compute the first and follow functions. That's what we will do now. So the definition of first function, if you recall, we say that a terminal symbol A belongs to first of alpha if from alpha in 0 or more steps, if we can generate an intermediate form like A beta, then the terminal symbol A belongs to first of alpha, and epsilon belongs to first of alpha if we can generate epsilon from alpha. Right? So towards this, so let's consider some simple base cases. So what is first of A, where A is a terminal symbol, then it is simply A. The second base case is this. First of epsilon is epsilon. So now we will take a slightly more involved case, that is we have a substitution rule like this. A goes to BC. If A goes to BC, and let's say if the terminal symbol A belongs to first of B, then what we have is from B in 0 or more steps, we can generate this intermediate form like A beta. So from this we can say from A we derive BC because we have the substitution rule, and from B we can generate A beta and C. So this whole derivation implies that A belongs to first of A. To summarize, if we have a substitution rule like A belongs to BC, and A belongs to first of B, together they imply A belongs to first of A. This is the first observation. So now let's look at the second case. The second case is we still have the substitution rule. A goes to BC, and what we have is epsilon belongs to first of B. So what it means is from B in 0 or more steps we can generate epsilon. So that means we can have this derivation A goes to BC, and in 0 or more steps we can arrive at C. From this what we can infer is if the terminal symbol A belongs to first of C, then the same terminal symbol A belongs to first of A2. The reason is if A belongs to first of C, then that means in 0 or more steps we can generate A beta, then that means A also belongs to first of A. So this is the second observation. That is, if epsilon belongs to first of B, then we have to consider the next non-terminal symbol C also. non-terminal symbol or terminal symbol, whatever it may be, we have to consider the symbol C also. Now let's look at another case. This is, let's go here. So again, we have the substitution rule. A goes to BC, epsilon belongs to first of B, and epsilon belongs to first of C. So what it means is from A, we have BC. In 0 or more steps, we can reduce the non-terminal symbol B to epsilon. And in 0 or more steps, we can reduce the non-terminal symbol C to epsilon. So overall, this implies that epsilon belongs to first of A. So that's all. So this is the basic idea behind the computation of the first sets. There's a question here. Let's see what's the question. Just give me a minute. All right. So this is the computing first of X. So we will summarize the discussion that we have seen in this slide. So if X is the terminal, then first of X is X. This is what we have seen. And even if X is if X is equal to epsilon, then also first of epsilon is equal to epsilon. And if X is a non-terminal symbol, and we have a substitution rule like this, then the first thing that we do is we consider the non-terminal symbol y1, and we include all non-epsilon symbols from first of y1 in first of X. And if epsilon is present in first of y1, then we consider y2. Similarly, if epsilon is present in first of y1, first of y2, first of yi minus 1, then we consider first of ya. And if epsilon is present in first sets of all yi, where I goes from 1 to k, then we include epsilon in first of X. And if X belongs to, and if there is a substitution rule like X goes to epsilon, then we add epsilon to first of X. So that's it. So these are the basic rules that we follow during the computation of first functions. Now let's try to apply this algorithm. Let's try to apply, it's not actually an algorithm, let's try to apply these rules and see how we can compute the first sets for various non-terminal symbols. So we have the grammar here, as you can see. So in order to compute first of S, we need to know what is first of A and what is first of B. And in order to compute first of A, we need to know first of B. And in order to compute first of B, we need to know what is first of A. So there is a circular dependency between the computations of the first functions for the non-terminal symbols A and B. So this circular dependency gives rise to problems. If there is no circular dependency, then we can kind of construct topologically sort the dependency graph and then compute the first functions in the appropriate order so that these dependencies will not cause any problem. But when there is a circular dependency, we get into trouble. That means the computation of A depends on computation of B, and the computation of B depends on the computation of A. In these cases, we take an approach called as fixed point approach for computing functions. So what is this fixed point approach? In this fixed point algorithmic approach, we start with some initial approximation for various sets that we have that we need to compute, and then we keep improving these sets. Then we keep improving these estimates. Like for example, here the initial estimate for the first of S, first of A, first of B, we are estimating them to be empty sets. And then we keep on updating these estimates. Like for example, here in step 1.1, so in step 1, what we do is we try to update the estimates of different, the first sets for different non-terminal symbols. It consists of 3 steps corresponding to 3 different non-terminal symbols. That is S, A, and B. So here in the step 1.1, to compute first of S contains first of A and first of B, but the current estimate of first of A and first of B is null sets. So when we take union of them, so first of S set will just be the same. It's not going to change. And then in the step 1.2, so first of A is dependent on first of B, but the current first of B is empty set. So that's all it has got. And in step 1.3, if you see, there are 2 substitution rules. One substitution rule uses the first of A to be included in the first set of B. And the second substitution rule says that epsilon should be present in the first set of B. So from here, you don't get much information, but the second substitution rule, B goes to epsilon, it tells us that epsilon should be included in the first set of B. Now we go to the second iteration. In the second iteration, so again, while computing first of S, we use the latest estimate of first of A, which is this, and the latest estimate of first of B, which is this. When we union them together, we include epsilon in the first set of S. So now in the step 2.2, so we would like to update the first set of A. So in order to update the first set of A, we use this information. Since epsilon is present in first of B, we can include A, the terminal symbol A, in the first set of A. Great, so this is good improvement. And then if you look at first set of B, first set of B depends on first set of A. We include the symbol A from the first set of A in the current estimate of, to get the new estimate for the first of B. So at the end of iteration 2, this is the latest estimates for different first sets for the non-terminal symbols. So again, if you see in step 3.1, so first of S contains first of A and first of B. So just use this. And what is first of A? First of A is dependent on first of B. It's not going to change. And how about first of B? So again, first of B depends on first of A. It remains the same. So at the end of the third iteration, this is the update. So let me use a different color. So at the end of this is the in iteration, at the end of first iteration, these are the different estimates for the first sets. And when we moved from first iteration to second iteration, so these are the estimates. And as you can see, there is an improve in the estimate for both for all the 3 non-terminal symbols. For the start symbol S, the new symbol that is included is epsilon. For the non-terminal symbol A, the new symbol that is included is A. And similarly for the non-terminal symbol B, the new symbol that is included is A. And when we moved from iteration 2 to iteration 3, this is iteration 3, at the end of iteration 3, the estimates for the first sets of A and B didn't improve, but the estimate for the first set of S has improved. So what did we do? We included the terminal symbol A in it. And at the end of iteration 4, if we repeat the same process, we see these are the estimates. And we can notice that these estimates didn't improve from the previous iteration. So when the estimates don't improve from the previous iteration, then that means the algorithm has stabilized. And if you go for do one more iteration also, it's not going to improve at all. So we say that the algorithm has converged, and we say these are the first sets associated with the different non-terminal symbols. So this algorithmic approach is what is called as a fixed point approach for computation of functions. So there are few questions that we would like to ask whenever we take a fixed point approach, fixed point iterative approach to compute functions. So the first question is, does the initial approximation matter? So of course, yes, because if you take so here we started with an under approximation. But if you start with an over approximation, that is, if you, instead of this here, if you start with an estimate like this is over approximation, then what happens? Then we will not be able to converge, or we will be converging to possibly an incorrect answer. So the initial approximation matters. Does the algorithm converge? That is the second question. So yes, the algorithm converges. The reason is, if you see from one iteration to another iteration, these sets are monotonically increasing. Initially, each of these sets, they contain here they contain 0 elements, 0, 0, the size of these sets. So here it is 0, 0, 1, the size of the set. So here if you see 1, 1, the size of the set is 2. And here if you see 2, 1, 2, here if you see 2, 1, 2. So the size of the sets are monotonically increasing. And they cannot, they will not shrink. The particular rules, the particular way in which we are composing, we are applying the rules, the sets cannot shrink, they can only grow. And they cannot grow indefinitely because, this set contains terminal symbols or the epsilon symbol, and they are finite. So these sets cannot keep on increasing. So at some point, so the algorithm has to converge. So that is the argument for convergence of the algorithm. How many iterations does it take to converge in the worst case? I want you to think about this question. So what is the worst case time complexity of this iterative approach? The fourth question is, does the number of iterations depend on the order in which we compute first x in a particular iteration? So here, if you see, we have computed first s within the iteration 1. We first computed first s, and then first a, and then first b. So does this order have an impact on the number of iterations required to converge? Let's try to answer this question by revisiting this example. So we have the same grammar here, and we want to compute the first sets for A, B, for the non-terminal symbols S, A, and B. And instead of computing the the first sets for the non-terminal symbols S, A, and B in the order, in the previous case, we come within an iteration, we started with S, and then we computed the first set for A, and then we computed the first set for B. But now we are starting with the computation of the first set for B, followed by A, and followed by S. So if you start with B, then we can immediately conclude that the epsilon symbol belongs to the first set of B. And this will have an immediate impact on the computation of the first set of A. We will include the terminal symbol A in the computation of, in the first set of A. And then, so first set of S, which depends on first set of A and first set of B, so it both A and epsilon are included in the first set of S. And then we repeat. So, and you can see by the end of iteration 2, the actual first sets for different non-terminal symbols are available, and we require one more iteration, that is iteration 3, to figure out that the solution has in fact converged. When we use this particular order to compute the first sets, then we required 4 iterations. But in this case, when we computed it in the order B followed by A followed by S, then we required 3 iterations. So by being clever about the order in which we compute the first sets for different non-terminal symbols within an iteration, we will be able to reduce the number of iterations required to converge. Good. So this is about computing first functions. So now we will see how to compute the follow functions. If you recall the definition of follow functions, so we say definition of the follow function, we say terminals, if you have a substitution, if there is a derivation like this from S, if you are able to generate something like alpha A beta, then just give me a minute. Let me see if current slide. Just 1 minute, guys. Okay, let me continue. So we say that we start with S, and if we have alpha A, then that means A belongs to follow of A. And in particular, remember that we are considering augmented grammars. So if you augment a grammar with the substitution rule, augment a grammar with the substitution rule, S prime goes to S dollar, then naturally what follows is this dollar symbol will always be present in the follow set of S. So this is the definition for the follow set, and we would like to compute the follow of different non-terminal symbols in the grammar. And the way we go about it is we again use an iterative algorithm for the same, iterative fixed point algorithm for the same. And what is the initialization step? The initialization step is follow of S contains dollar, because we are working with the augmented grammar with the substitution rule S prime goes to S dollar. And the initial estimate of follow sets for different non-terminal symbols is empty set. So let's look at, so there are 3 rules here which we would like to follow while computing the follow sets. So the first rule is this. It's associated, let's look at this particular rule. If there is a production A goes to alpha beta, then everything in follow of A is in follow of B. Why is this? So So let's say starting from S, in 0 or more steps, we are able to generate an intermediate form like this. So what this means is the terminal symbol A is present in the follow set of A. But then we have the substitution rule. A goes to alpha beta, so alpha B, A, comma 2. So all this derivation, this whole derivation, this implies if we have a production like this, and if A belongs to follow of A, then A belongs to follow of B2. This is the first observation. This is the simplest observation. Next, consider the case we have a substitution rule like this. A goes to alpha B beta, and so let's consider this case. So we have A goes to alpha B beta. So let's consider a derivation like this. And we have the substitution rule, alpha B let me check. We have the substitution rule. So let's replace this A with alpha. So we have gamma 1, alpha B beta, gamma 2, okay. And from beta, we can generate yeah, it's simple. Yeah. So I think let me I think I kind of hold. This rule is fairly simple actually. Let's start again. So we have the substitution rule. A goes to alpha B beta. So we start from S. In 0 or more steps, we generate an intermediate form like this, gamma 1, A, gamma 2. And then we replace this gamma 1, A with alpha B beta, gamma 2. And so from this, we should be able to generate something like A beta prime gamma 2. So this, there are too many symbols, but the idea is very simple. So there is a sequence of derivations in which we can generate an intermediate form like this. We can generate an intermediate form like this. And whatever that is present in first of beta is also present in the follow of B. Okay. So from beta, you are able to generate an intermediate form like A beta prime. So then that means A belongs to first of beta. So whatever that is present in first of beta, whatever that is present in first of beta is present in follow of B. Whatever that is present in first of beta is present in follow of B except epsilon symbol. Right? Because epsilon can never be present in the follow sets. So whatever that is present in first of beta is present in follow of B. If you make it similar, I would like you to give the second rule as a homework here. That is, if first of beta contains epsilon, then everything that is present in follow of A is in follow of B. So this rule, I am giving this as a homework. So prove this. If first of beta contains epsilon, then everything that is present in follow of A is present in follow of B. All right. So these are the three rules that we repeatedly apply to compute the follow sets. So now let's take an example. So this is the example that we have. So we have S goes to, this is the grammar that we have. And we would like to compute the first sets for, the follow sets for different non-terminal symbols. So we start with the initial approximation. That is, the follow of S contains dollar, because this is the augmented grammar. We are working with the augmented grammar. And the estimate for the follow set of B and the follow set of A is empty set. And when we look at the follow set, so in iteration 1.1, we would like to update the follow set for S. And it is not going to change. All right, the follow set for S, it is going to remain the same. So if you want to apply which rule we would like to apply to improve the follow set of S, we would like to apply this rule in order to improve the follow set of S. That is, whatever that is present in follow of A is also present in follow of S. But at this point in time, the follow of A is empty set. So we are not able to improve the follow set of S at this point in time. But if you look at the follow of B contains whatever that is present in follow of S is present in follow of B too. So we apply that rule to improve the follow set for B in iteration 1.2. And now if you look at in iteration 1.3, the follow set of A consists of, we want to compute the follow set of A. And the follow set of A, it consists of whatever that is present in first of B, okay, excluding epsilon. So whatever that is present in first of B is present in the follow of A. Okay. And if epsilon is present in first of B, then whatever that is present in follow of S is also present in follow of A. So what happens is we use, yeah, again, where is yes? This is yes. So we use this dollar to update here. So like this, so at the end of iteration 1.3, this is the estimate that we have. So we go to iteration 2 and we apply the same rules with the new improved estimates at the end of iteration 1. So this is, these are the values at the end of the iteration 1. So we use these improved estimates to compute to update or improve the follow sets in the second iteration. I will not go through these rules again. I would like you to check that in fact, all these, the application of rules is correct. At the end of iteration 2, so the estimates turns out to be this. And at the end of iteration 3, the estimates will be this. So there is no improvement from this iteration and from this iteration. So we say that the algorithm stabilized or converged. So I really would like you to appreciate this particular approach that we are taking to compute these follow functions. So this approach is called as an iterative fixed point approach. iterative fixed point algorithmic approach. So this is how we compute the follow functions. Let's keep going. So this is the grammar that we have been working with. So a homework problem for you is compute the follow sets for the different non-terminal symbols occurring in this grammar. This is a homework problem for you. So now what we will do is we will use this idea about constructing. Now we know how to construct first and follow sets, right? So we use these ideas to compute the first plus sets for different substitution rules. And from that we construct what is called as a predictive parsing table. So here we have this parsing table where the columns are marked with are labeled with non-terminal symbols. Sorry, where the rows are labeled with non-terminal symbols and columns are marked with terminal symbols. So if the current non-terminal symbol to expand is E, and if the current look ahead symbol is ID, we would like to apply the substitution rule E goes to TE prime. If the current non-terminal symbol is plus, then there is no substitution rule we can apply, then that means it's a parsing error. Similarly, if the current non-terminal symbol to expand is E and the look ahead symbol is left parenthesis, then the substitution rule to apply is E goes to TE prime. So in general, if you see, what we do is we compute first plus of TE prime, first plus of TE prime. And so it turns out that the first plus of TE prime, so actually let me E goes to TE prime, and it turns out this set is ID plus and left parenthesis. So we want to apply this substitution rule E goes to TE prime if the look ahead symbols are ID plus or left parenthesis. On the contrary, if the current look ahead symbol is anything but these three symbols, and the non-terminal symbol to expand is E, then we say that there's a parsing error. That means the input is not a valid string described by the context-free graph. So now let's try to see what is happening with the non-terminal symbol E prime. If you consider the non-terminal symbol E prime, so the first place of what is first place of E prime going to plus TE prime? It is plus. Because first of plus TE prime, it contains the symbol plus only. So what happens is in this table, we make the entry that when the current non-terminal symbol to expand is E prime and the look ahead symbol is plus, we have to use this substitution. Similarly, if you see first plus of E prime goes to minus TE prime, then you have minus. So we make this entry, the entry corresponding to the row E prime and column minus is E prime goes to minus TE prime. All right, let me. So let's take one more interesting example. So the example is what is first place of E prime going to epsilon. If you consider first place of E prime going to epsilon, so what happens? So epsilon is present in first of in the first set. So recall, if this is the case, so if we have A goes to A goes to alpha, and so the first plus of this, let me use a shorthand, F plus of this is equal to first of alpha union follow of A. If epsilon belongs to first of alpha. So in this particular case, epsilon trivially belongs to first of alpha because alpha is nothing but epsilon. And so what we do is we have to include follow of A in the first plus set. And if you compute follow of E prime, it turns out follow of E prime is equal to follow of E prime. This is equal to, it contains these two, left parenthesis and dollar. How is it the case? We can easily make a note, like for example, from S prime, we can get E dollar, and E is nothing but TE prime dollar. So dollar belongs to follow set of E. And how do we know that right parenthesis is present in the follow set of E prime? So if we kind of just focus on this particular substitution rule, if you replace E with TE prime, then we get TE prime right parenthesis. That right parenthesis is present in the follow set of E. So overall what it means is that the first place of E prime giving rise to epsilon, so this set is equal to this. So now what we do is, so in these entries corresponding to the right parenthesis and dollar in the row associated with the non-terminal symbol E prime, we fill these substitution rules. So this is how we construct the whole predictive parsing table. Once we have this predictive parsing table, we can refer to this predictive parsing table to see how we can to guide the parser in the parse tree construction process. Let's try to take an example and understand what is happening here. Let's with how this parsing process proceeds. So let's say the input string is ID plus ID dollar. So what we do is, so we have a stack. So let's say in the stack, remember we do this parsing using a push down automata. In the parser, in the stack, we have this dollar symbol already pasted, that is the stack marker. And then we have the input. This is the input, the current input pointer is ID. And E is the, so what happens is if the current, so actually what we do is, we keep the start symbol E. So if the top of the stack is E, and if ID is the current look ahead symbol, what we do is we pop this E out from the stack. We pop E out from the stack and push TE prime, because this is a substitution rule that we have to apply. So we pop TE prime and we pop it in the reverse order. This is the state of the stack. So we don't have enough space here, so pardon me for for all the, it's a bit cluttered, but I want you to see the idea. And if the current top of the stack is T and the input symbol is ID, we pop T out and we push FT prime in the stack. So we have dollar E prime, T prime, and F. This is what we have. And if the current top of the stack is F, and if the current input symbol is ID, then the substitution rule to apply is this. So we pop F out and we push ID in. And if the current top of the stack is ID, and if we have ID here, there is a match. So you pop ID out from the stack and we advance the input pointer to the next plus symbol. This is the state of the stack. And this is the current input symbol. If the top of the stack is T prime, and if the next input symbol is plus, if the current look ahead symbol is plus, we apply the substitution rule, T prime goes to epsilon. So what we do is, so this is what we get. Good. And if the top of the stack is E prime, and if the current input symbol is plus, we have to apply the substitution rule. So you pop E prime out, dollar E prime T plus. This is the state of the stack. So now if the top of the stack is plus and the current input symbol is plus, so you pop this plus out from the stack. And we advance the input pointer to the next. So this is how the parsing process proceeds. By the time what happens is, by the time this whole parsing process succeeds, so the stack state will be dollars, everything will be gone, and the input pointer will be pointing to dollar. These two dollars will match, and that concludes successful parsing process. So this whole idea can be nicely summarized in this picture. So we have the input here, this is the input, and then here this is the stack, which helps the parsing algorithm to keep track of the derivation process. And this is the core predictive parsing program. And the most important thing is what changes from one grammar to another grammar is this parsing table. The stack remains the same, and of course, depending upon what input that we want to parse, the input changes. So these are just data structures. Okay, so this is going to remain the same. This is going to remain the same. The core algorithm remains the same, and what changes from one grammar to another grammar is the parsing table. So then that means we have a automatic parser generator. So the whole program remains the same, and you just give me a context-free grammar, and associated with that context-free grammar, we just generate the parsing table, and that's it. We have a parser for the new grammar. So this is an approach for generating top-down predictive parsing, predictive parsers with no backtracking. Okay. Let's continue. So let's consider, so in a couple of classes back, I said, no, when there are ambiguities in the grammar, we can kind of, there are two approaches to take care of it. One approach is to rewrite the grammar, other approach is to tell the parser to lean towards a particular parsing strategy. So the grammar that you are seeing here, it captures the problem that is associated with the if-then-else statements. So if we go ahead and construct a parsing table for this grammar, it turns out that a particular entry in the parsing table, it has two entries. That is, if the current non-terminal symbol to expand is S prime, and if the current look-ahead symbol is E, we have two approaches. Okay, so either we can use the first substitution rule or we can use the second substitution rule. It's a problem because when there are two possibilities, then theoretically speaking, the grammar is not LL1 parsable. So what we do is between these two substitution rules, we tell the the parser to always lean towards the first substitution rule or lean towards the second substitution rule. And when we do that, what happens is the kind of parse trees that are constructed, they will always be take certain pattern. And we want to, whether we want to tell the parse tree, the parser, to take the first substitution rule or the second, or use the second substitution rule always, It depends on what kind of semantics that we would like to give to the input programs. We use a similar approach. We use a similar approach even in the bottom-up parsers, which we will discuss later on. There can be ambiguity in the grammar, so that kind of gets reflected during the time of parsing. But we tell the parser to lean towards some parse trees. This may not be possible all the time, but in some cases this strategy works out. So depending upon the context, when there is an ambiguity like this, you have to understand the source of ambiguity and take the appropriate decision. Either you may have to change the context-free grammar to resolve the ambiguity, or you can tell the parser to resolve the ambiguity by leaning towards a certain substitution rule during the process of parse tree construction. So finally, to conclude the discussion on this, there are two things that I would like you to see. All right, so with all these constraints on the LL1 grammars, are they any powerful than the regular grammars? What are regular grammars? Regular grammars are those which describe regular languages. So if you consider, in order to answer this question, if you consider this simple grammar, so this grammar, it generates the language. The language of this grammar is isomorphic to this language. And you know from the automata theory, this is the first example that you see. This is the first example of a non-regular language you will see while studying regular expressions, regular languages, etc. And you prove that this language is not regular by using the pumping lemma of regular expressions. So using pumping lemma, you prove this is not regular. But on the contrary, you can easily check this is a LL1 grammar because the first place set of this, first place of this, it is left parenthesis. And first place of epsilon, this is not epsilon, this is right parenthesis. Because first place of this contains follow of s, and follow of s contains this and actually even dollar. Okay. So this is an example of a grammar which is not regular but still LL1. So I said at the beginning of this class, there is one particular grammar which bothered us before. That is 0s0, 1s0, epsilon. So when we were studying this grammar, the problem that we encountered is we know when to use the first substitution rule, when to use the second substitution rule, but we don't know when to use the third substitution rule. How can we theoretically come to a conclusion that this is a problematic grammar to parse, to come up with a backtrack-free parser? So what is first plus of 0 is 0? It is 0. First plus of 1 is 0 is 1. First plus of epsilon. So since it's epsilon, whatever that is present in follow of s, so actually this we should be s goes to this. S goes to epsilon. Whatever that is present in follow of s is present in this first plus set. So now we can see that the first plus sets of the first substitution rule, this substitution rule and this substitution rule, they intersect on 0. So if the current look-ahead symbol is 0, we don't know whether we should be using the first substitution rule or the third substitution rule. Similarly, if the current look-ahead symbol is 1, we don't know whether we should be using the second substitution rule or this substitution rule. So these two substitution rules, they conflict on the input symbol 1, and the first and the third substitution rules, they conflict on the input symbol 0. So that is the reason this grammar is not LL1 parsable. But on the contrary, if we change this grammar to this grammar 0s0, 1s0, and c, where c is a constant, then what happens is the first plus of s goes to c is c. All right. Then now what happens is the first place set of any of these substitution rules, they don't intersect with each other, and the grammar becomes LL1 parsable. So this concludes our discussion on LL1 parsing. What we didn't cover as a part of this lecture is error recovery techniques while doing LL1 parsing. Okay, so let's stop here for today. And in the next class, we will study about abstract syntax trees, the structure of abstract syntax trees we'll study in the next class.